The sun lights our days, warms our planet, and makes life possible. But like all stars, it will not last forever. One day, its life will end, and with it, all life on Earth will too. Welcome to Boring Stuff. Tonight, we'll take a calm, quiet journey through the life and inevitable death of our sun. How it was born, how it shines, and why the fate of Earth is already sealed in the stars. So get comfortable and let's begin. The sun is a star. To us on Earth, it may seem unique, the bright disk in the sky that brings light, warmth, and life. But in the wider universe, it is one of countless stars, each following the same basic life cycle dictated by physics. No star lasts forever. Every star is born, burns for a time, and ultimately dies. The sun's eventual destruction is not a distant possibility. It is an inevitable stage in this natural cosmic process. Stars begin their lives inside large, cold clouds of gas and dust called molecular clouds. These clouds exist in many regions of the galaxy, shaped by the movements of interstellar matter. At some point, a disturbance, such as a nearby supernova or the gravitational tug of another cloud, causes part of the cloud to collapse under its own gravity. As the gas collapses, it fragments into dense clumps, each of which can become a new star. About 4.6 billion years ago, such a collapse occurred in a region of our galaxy that eventually gave birth to the sun. As the cloud collapsed, its center grew denser and hotter. Gravity pulled material inward, creating a core where temperatures climbed to millions of degrees Kelvin. When the core temperature passed roughly 10 million Kelvin, hydrogen atoms in the core began to fuse together in a process called nuclear fusion. This was the birth of the sun as a star. The ignition of nuclear fusion marked the start of its life cycle on what is called the main sequence, the long, stable period in a star's existence. In this phase, hydrogen nuclei fuse into helium, releasing vast amounts of energy. This energy creates outward pressure that balances the inward pull of gravity, keeping the star stable. The Sun is a main sequence star of spectral type G2V, a yellow dwarf. Stars on the main sequence spend the majority of their lives fusing hydrogen. For a star of the Sun's mass, this phase lasts roughly 10 billion years. The Sun is now about 4.6 billion years into this phase, meaning it is nearly halfway through its stable life. During this main sequence period, the Sun shines steadily, maintaining the same general size and temperature. Its energy output is stable enough to sustain life on Earth. But the fusion process is slowly changing the composition of the core. As hydrogen is fused into helium, the core becomes denser and hotter. Over millions of years, the Sun's energy output gradually increases. Measurements suggest that the Sun is already about 30% more luminous than it was when Earth first formed. This slow increase will continue. In roughly 1 to 1.5 billion years, the rising luminosity will likely cause Earth's climate to shift dramatically, evaporating the oceans and ending complex life long before the Sun's actual death. The life cycle of stars depends strongly on their mass. The Sun's mass is about 1.99×1030 kilograms, enough to sustain hydrogen fusion for billions of years, but not enough to end in a violent supernova. More massive stars live much shorter lives, burning through their fuel rapidly and ending in explosive deaths. Smaller stars, like red dwarfs, can burn for trillions of years, far longer than the current age of the universe. Because the Sun falls in the middle range of stellar masses, its life follows a relatively well-understood pattern. It will remain on the main sequence for roughly another 5 billion years. But this stage cannot continue indefinitely. As the core's hydrogen runs low, fusion will slow, the balance of forces will shift, and the Sun will begin its transition into the next phase of its life, one that will ultimately lead to its destruction. The key to understanding the Sun's future is the nature of nuclear fusion itself. Fusion can only occur when temperatures and pressures are high enough to overcome the repulsive forces between atomic nuclei. For the Sun, hydrogen fusion is relatively efficient. It requires only about 10 million Kelvin. But fusing heavier elements, like helium into carbon, requires much higher core temperatures, closer to 100 million Kelvin. Once the Sun's core runs out of hydrogen, its outer layers will no longer be held up by fusion pressure. Gravity will cause the core to contract, heating it further. This contraction will trigger new phases of fusion, but each stage is shorter and less stable than the last. The entire process is controlled by well-understood laws of physics, gravitation, thermodynamics, quantum mechanics, and the behavior of plasma. These laws dictate the limits of what is possible for a star of the Sun's mass. No amount of natural variation or random chance can change the basic outcome. The Sun's eventual death, through expansion into a red giant, the ejection of its outer layers, and the formation of a white dwarf, is not just likely. It is certain. Observations of other stars at different stages of their life cycles confirm this model. Astronomers have observed many red giants, planetary nebulae, and white dwarfs in various parts of the galaxy. These observations match the predictions of stellar evolution theory. The Sun's future is simply the next step in this universal pattern. In summary, stars are not permanent. The Sun is not an exception. Its death is built into its nature from the moment of its birth. The same gravity that once caused the Sun to form from a collapsing gas cloud will one day lead to its collapse and transformation. The nuclear processes that give the Sun life also set a limit on its lifetime. The Sun is now stable, but only for now. Time, physics, and the finite nature of its fuel supply guarantee that one day it will change, and that change will bring an end to life on Earth as well. About 4.6 billion years ago, long before the formation of Earth, the region of the Milky Way galaxy that we now inhabit was home to a giant molecular cloud. This was a cold, dense collection of gas and dust, mostly hydrogen, with smaller amounts of helium and trace elements left over from earlier generations of stars. These clouds drift through galaxies, sometimes for millions of years, until a trigger causes them to collapse and form new stars. In the case of the Sun's formation, the exact trigger is not known, but one plausible scenario is the shock wave from a nearby supernova, the violent death of a massive star, which compressed a portion of the molecular cloud. This sudden compression tipped the balance between gravity and internal pressure. Gravity began to pull the gas and dust inward, causing the cloud to fragment into smaller clumps, each with the potential to become a new star. One of these clumps contained enough mass, about 1.99 kilograms, to eventually form what we know today as the Sun. As gravity pulled material inward, the collapsing clump became denser and hotter. Conservation of angular momentum caused it to spin faster as it contracted, much like an ice skater pulling in their arms to spin faster. The rotating mass flattened into a disk with a dense core at the center, a structure known as a protostellar disk. At this stage, the central core was not yet a true star. It was what astronomers call a protostar. In this phase, gravitational contraction was the primary energy source. As the gas compressed, its temperature and pressure increased. Surrounding the protostar, the disk of dust and gas gradually began to thin, with much of its mass falling onto the growing central object, while some remained in the disk, material that would later form planets, moons, asteroids, and comets. As the core continued to contract, its temperature climbed into the millions of Kelvin. Once the core reached roughly 10 million Kelvin, conditions were finally sufficient for nuclear fusion to begin. Hydrogen nuclei, protons, began to collide with enough force to overcome their mutual electrostatic repulsion and fuse into helium. Each fusion event released energy in the form of gamma rays, as well as neutrinos. This moment marked the true birth of the Sun as a star. The onset of nuclear fusion provided a new energy source, one that was vastly more efficient than gravitational contraction. The gamma-ray photons produced in the core took hundreds of thousands of years to work their way outward, being absorbed and re-emitted countless times by particles in the dense interior. Eventually, the energy reached the surface and escaped into space as visible light and other forms of electromagnetic radiation. At the same time, the energy from fusion created outward pressure that counteracted gravity. A balance was achieved. The inward pull of gravity was exactly balanced by the outward pressure of radiation and hot plasma. This state of equilibrium is called hydrostatic equilibrium. Once this balance was reached, the Sun entered the long, stable phase of its life known as the main sequence. Meanwhile, in the surrounding disk, the remaining dust and gas were gradually swept away by solar winds and radiation pressure from the newborn Sun. However, before this material dissipated entirely, some of it coalesced into solid bodies. Through a process of accretion, dust grains stuck together, forming larger and larger clumps. Over time, these clumps grew into planetesimals, then protoplanets, and eventually the planets of the solar system. The Sun's early life was not completely stable. Young stars often experience periods of variability, with strong stellar winds, flares, and magnetic activity. The young Sun likely passed through a T-Tauri phase, characterized by intense winds and rapid rotation, which helped shape the final architecture of the solar system. By the time the Sun was about 100 million years old, it had settled into a relatively stable state. The planet-forming disk had mostly cleared, leaving behind the familiar 8 planets, their moons, and a scattering of smaller objects. From this point on, the Sun's evolution followed the well-understood path of main sequence stars. It burned hydrogen in its core at a steady rate, producing a constant output of energy that has supported life on Earth for billions of years. The formation of the Sun is part of a larger cycle of stellar birth, life, and death that has been ongoing in the universe for more than 13 billion years. The material in the original molecular cloud from which the Sun formed was not purely new matter. It contained elements forged in earlier stars, including heavier elements like carbon, nitrogen, oxygen, and iron, which are essential for rocky planets and for life as we know it. These elements were created in the cores of older stars and scattered into space by supernovae. In this sense, the Sun, and everything in the solar system, is made from recycled stardust. The current understanding of star formation is based on decades of observation and theory. Astronomers observe molecular clouds in our galaxy, such as the Orion Nebula, where new stars are still forming today. They see protostars in various stages of collapse. They observe the outflows, jets, and disks around young stars. These observations match the theoretical models, confirming the basic sequence of events that led to the Sun's birth. The entire process of the Sun's formation, from cloud collapse to stable main sequence star, took about 50 million years. In cosmic terms, this is a brief period, but the consequences have lasted far longer. The Sun has been shining steadily for the past 4.6 billion years and will continue to do so for several billion more. Understanding how the Sun was born helps us see it not as an eternal object, but as part of a dynamic universe. Its birth was one event in a chain of cosmic history. Its life, though long, is finite. And its future evolution, like its birth, is governed by the laws of physics that shape all stars. The Sun appears to us as a smooth, bright disk in the sky. But beneath its surface, it is a complex and layered structure governed by the interaction of gravity, pressure, temperature, and electromagnetic forces. Understanding this internal structure is key to understanding how the Sun produces its energy and how that energy reaches Earth. At the core of the Sun, extending outward to about 25% of its radius, is the site of nuclear fusion. The temperature here exceeds 15 million Kelvin, and the pressure is more than 200 billion times the atmospheric pressure at Earth's surface. Under these extreme conditions, hydrogen nuclei, protons, have enough kinetic energy to overcome their natural repulsion and fuse into helium nuclei. Each fusion reaction releases a small amount of mass, which is converted into energy according to Einstein's famous equation, E equals mc2. Although the mass lost in any single reaction is tiny, the sheer number of reactions, approximately 1038 per second, results in a constant and enormous output of energy. Moving outward from the core, the next major layer is the radiative zone. This extends from the outer edge of the core to about 70% of the Sun's radius. In this region, energy is transported not by the movement of matter, but by the process of radiative diffusion. High-energy photons produced in the core are repeatedly absorbed and re-emitted by ions in the dense plasma. This random walk of photons through the radiative zone is extremely slow. On average, it takes a photon thousands, possibly up to 1 million, years to travel from the core to the top of this layer. During this time, the energy of the photons shifts downward from gamma rays toward X-rays and eventually to ultraviolet light. The temperature in the radiative zone decreases with distance from the core, ranging from about 7 million Kelvin near the core boundary to about 2 million Kelvin at the top of the radiative zone. The pressure also decreases steadily. Beyond the radiative zone lies the convective zone, which extends from about 70% of the Sun's radius to its visible surface, or photosphere. In this layer, the temperature and density drop to the point where radiative diffusion becomes inefficient. Instead, energy is transported primarily through convection. Convection is the process by which hotter, less dense plasma rises, while cooler, denser plasma sinks. This movement creates convection currents, enormous loops of plasma cycling through the convective zone. These convective motions can be seen at the solar surface in the form of granulation, small, bright cells surrounded by darker lanes. The convective zone plays an important role in shaping the sun's magnetic field. As the plasma moves, it drags magnetic field lines with it, twisting and tangling them. This process is responsible for many of the sun's magnetic phenomena, including sunspots, solar flares, and coronal mass ejections. The photosphere is the layer we see when we look at the sun with appropriate filters. It is about 500 kilometers thick and has a temperature of roughly 5,500 degrees Celsius, or 5,800 Kelvin. Although the photosphere appears solid to the eye, it is actually a region of hot plasma that becomes progressively more transparent with altitude. The light that escapes from the photosphere is what illuminates the Earth and drives our climate. The spectrum of this light is very close to that of an ideal blackbody, an object that absorbs and emits all wavelengths of radiation, with a peak in the visible range. Above the photosphere lies the chromosphere, a layer of the sun's atmosphere that extends a few thousand kilometers upward. The chromosphere is less dense than the photosphere, and its temperature rises from about 4,500 Kelvin at the base to roughly 20,000 Kelvin at the top. The chromosphere is visible during solar eclipses as a reddish glow around the sun's darkened disk. It is also the site of spicules, narrow jets of plasma that shoot upward at speeds of up to 100 kilometers per second. The outermost layer of the sun's atmosphere is the corona. Extending millions of kilometers into space, the corona is remarkably hot, with temperatures ranging from 1 to 3 million Kelvin. This is much hotter than the underlying photosphere, a phenomenon that is still not fully understood but is thought to involve magnetic heating and wave energy. The corona is the source of the solar wind, a continuous stream of charged particles that flows outward into the solar system. The solar wind interacts with the magnetic fields of the planets, producing phenomena such as Earth's auroras. One puzzling aspect of the corona is its low density. Despite its high temperature, it contains very little matter. This means it emits much less visible light than the photosphere, making it difficult to observe except during eclipses or with specialized instruments like coronagraphs. Each of these layers, core, radiative zone, convective zone, photosphere, chromosphere, and corona, plays a critical role in the sun's structure and behavior. Together, they form a dynamic system where energy generated deep within is transported outward and eventually radiated into space. The layered structure of the sun is not static. It evolves slowly over time as the sun ages and burns through its nuclear fuel. As the core's hydrogen supply diminishes, the core will contract and heat up, altering the temperature gradients in the radiative and convective zones. These changes will eventually trigger the sun's transition into its red giant phase. For now, however, the sun remains in a stable balance. The outward flow of energy from the core matches the gravitational forces pulling inward. This balance allows the sun to shine steadily, a constant source of energy for Earth and the solar system. Understanding the sun's layered structure helps explain why it behaves the way it does, why it shines, how it evolves, and what will ultimately lead to its demise. At the heart of the sun, nuclear fusion powers everything. Without it, the sun would be dark, cold, and inert. Fusion is the process that allows the sun to generate energy steadily over billions of years. Energy that supports life on Earth, drives the solar system's dynamics, and shapes the sun's evolution. Nuclear fusion occurs in the sun's core, where the conditions are extreme. The core's temperature exceeds 15 million Kelvin, and the pressure is more than 200 billion times Earth's atmospheric pressure at sea level. The density of the core is around 150 times that of water. These conditions are necessary because fusion involves forcing positively charged atomic nuclei, protons, to collide and merge, overcoming the natural repulsive force between them known as the Coulomb barrier. Under normal conditions, protons repel one another due to their positive electric charge. At room temperature and typical pressures, this repulsion cannot be overcome. However, at the temperatures and pressures found in the Sun's core, protons move at extremely high speeds. Occasionally, when they come close enough, quantum tunneling allows them to leak through the Coulomb barrier and fuse. In the Sun, the dominant fusion process is called the proton-proton chain reaction. This series of nuclear reactions converts hydrogen into helium and releases energy in the process. The sequence works as follows. Two protons, hydrogen nuclei, collide and fuse to form a deuterium nucleus, one proton and one neutron, while releasing a positron and a neutrino. This step is rare because it requires one proton to undergo beta plus decay, converting into a neutron. The deuterium nucleus then fuses with another proton to form helium-3, two protons and one neutron, emitting a gamma-ray photon. Two helium-3 nuclei eventually collide, forming a helium-4 nucleus, two protons and two neutrons, and releasing two protons back into the plasma. The net result of this chain is that four protons are converted into one helium-4 nucleus. During this process, about 0.7% of the mass of the original protons is converted into energy. This is a direct application of Einstein's mass-energy equivalence principle, E equals mc2. The energy released manifests as high-energy photons, gamma rays, kinetic energy of particles, and neutrinos. The amount of energy produced is enormous. The Sun fuses about 600 million metric tons of hydrogen into helium every second. This process releases approximately 4,1026 watts of energy, equivalent to the output of nearly 100 billion 1 megaton hydrogen bombs every second. However, this energy is spread evenly across the entire Sun and radiates outward smoothly. Gamma-ray photons produced in the core do not travel directly to the surface. Instead, they undergo a slow, random walk through the dense plasma of the radiative zone. They are repeatedly absorbed and re-emitted by ions and electrons. This diffusion process takes an extremely long time. It is estimated that a photon can take anywhere from 10,000 to 1 million years to migrate from the core to the edge of the radiative zone. During this journey, the photon's energy decreases. By the time it reaches the convective zone and, later, the photosphere, its wavelength has shifted from gamma rays to visible light and lower energy forms of radiation. As energy flows outward, the Sun remains in hydrostatic equilibrium. The gravitational force pulling inward is balanced by the outward pressure of the hot plasma and radiation. This balance is self-regulating. If fusion in the core were to increase, the resulting increase in outward pressure would expand the Sun slightly, lowering the core temperature and reducing the fusion rate back to equilibrium. If fusion slowed, the core would contract, heating up and increasing fusion. This dynamic balance allows the Sun to shine steadily. The neutrinos produced in fusion reactions are different from photons. Neutrinos interact only very weakly with matter. Once produced, they travel outward at nearly the speed of light and escape the sun in seconds. Billions of solar neutrinos pass through every square centimeter of Earth and our bodies each second. These neutrinos are important evidence that fusion is occurring as predicted in the core. Experiments such as the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada have detected solar neutrinos directly. These measurements confirm that nuclear fusion powers the sun, validating the models of solar physics. It is also important to note that the fusion process gradually changes the composition of the sun's core. Initially, the core was composed almost entirely of hydrogen. Over billions of years, fusion has built up helium in the core. Today, after 4.6 billion years, the core is estimated to be about 60% helium by mass. As the core's helium fraction increases, the rate of fusion adjusts. The core contracts slightly, increasing temperature and pressure, which in turn raises the fusion rate to maintain equilibrium. This is why the sun's luminosity has gradually increased over time. It is now about 30% brighter than when it first formed. Eventually, as hydrogen becomes depleted in the core, fusion will slow. The sun will no longer be able to maintain hydrostatic equilibrium in its current form. The core will contract and heat further, triggering new stages in the sun's evolution, most notably expansion into a red giant and eventual death as a white dwarf. The efficiency of the proton-proton chain is highly temperature-dependent. At the sun's core temperature of 15 million Kelvin, the process proceeds steadily. In more massive stars, core temperatures are higher, and a different fusion process, the CNO cycle, becomes dominant. In lower mass stars, the proton-proton chain remains the primary mechanism, but at a slower rate. Thus, the sun's mass and core temperature determine the specific fusion process that powers it. They also determine how long the sun can remain in the main sequence phase. For a G2V star like the sun, the main sequence lifetime is about 10 billion years. Having passed about 4.6 billion years of that span, the sun is roughly halfway through its hydrogen-burning stage. Without fusion, the sun would not shine. It would not produce light or heat. It would not drive the complex weather systems on Earth or sustain life. The sun's stability, brightness, and lifespan are all consequences of the proton-proton chain operating in the core. Fusion is a universal process in stars, not unique to the sun. Observations of stars of different masses, ages, and compositions across the galaxy all show patterns that match the predictions of fusion-driven models. Laboratory experiments in nuclear physics also support the theory. In short, fusion is the engine of the sun. It is the process that makes the sun what it is, a shining, life-giving star in the vast darkness of space. The sun shines because of nuclear fusion. Deep in its core, hydrogen atoms fuse to form helium, releasing energy that powers the sun's light and heat. But this process cannot continue forever. The hydrogen fuel in the core is finite. Eventually, it will run out, and this fact alone guarantees that the sun's current stable phase will come to an end. The fusion reactions in the sun's core follow the proton-proton chain. Every second, about 600 million metric tons of hydrogen are converted into helium. The total mass of the sun is about 1.999 × 1030 kilograms, and roughly 10% of that mass, about 109.28 kilograms, is contained in the core where temperatures and pressures are high enough for fusion to occur. This means that, while the Sun is massive, only a fraction of its total mass is actively involved in the fusion process at any given time. The outer layers are cooler and do not contribute to fusion. The Sun has been converting hydrogen into helium for about 4.6 billion years, and in that time it has used up roughly half of the available hydrogen in its core. As hydrogen atoms fuse into helium, the composition of the core changes. Hydrogen is a light element, consisting of one proton per nucleus. Helium, on the other hand, consists of two protons and two neutrons. This change in composition has several effects. First, helium atoms are more massive and occupy less volume than the original hydrogen atoms. As helium builds up in the core, the density increases. Second, because helium does not participate in the proton-proton chain under current core conditions, the amount of available hydrogen decreases over time. As the hydrogen fraction in the core drops, fewer fusion reactions occur in any given volume. To compensate, the core slowly contracts under the force of gravity. This contraction increases the temperature and pressure, which in turn boosts the rate of fusion among the remaining hydrogen. This feedback process ensures that the Sun's luminosity has gradually increased over time. When the Sun first settled onto the main sequence, its brightness was about 70% of its current level. Today, it is about 30% brighter than it was 4.6 billion years ago. This gradual brightening will continue as the core hydrogen becomes more depleted. Models of stellar evolution show that in about 1 to 1.5 billion years, the Sun's increasing luminosity will cause Earth's climate to change significantly. Higher temperatures will likely lead to the evaporation of the oceans and the loss of Earth's ability to support complex life. This will happen well before the Sun fully exhausts its core hydrogen. The final stages of core hydrogen depletion will occur roughly 5 billion years from now. At that point, the Sun will no longer be able to sustain the proton-proton chain at the current rate in the core. Once hydrogen fusion slows, hydrostatic equilibrium will break down. The outward pressure of fusion-generated energy will no longer balance the inward pull of gravity. The core will begin to contract further under its own weight. As the core contracts, its temperature will rise. The outer layers of the Sun, in contrast, will respond differently. They will expand and cool, transforming the Sun from a stable main-sequence star into a red giant. This transition marks the beginning of the end for the Sun's current phase. The shift from core hydrogen fusion to the red giant stage is an inevitable consequence of the finite hydrogen supply. No star can maintain core hydrogen fusion forever. It is important to note that the fusion process depends sensitively on temperature. The proton-proton chain operates efficiently only above about 10 million Kelvin. As the core contracts and heats up, new fusion processes will become possible. For example, when temperatures reach roughly 100 million Kelvin, helium nuclei can begin to fuse into heavier elements through the triple alpha process. However, this phase will be brief and unstable compared to the main sequence phase. The core's helium supply is also finite. Once core hydrogen fusion ends, the Sun will enter a series of short-lived evolutionary stages that cannot restore its former stability. The precise timing of these events is well constrained by astrophysical models. The Sun's mass, composition, and structure are known with high accuracy, allowing scientists to calculate its future evolution with considerable confidence. Observations of other stars also provide strong confirmation of these models. Astronomers have observed stars of various masses at different stages of their life cycles. The behavior of these stars matches theoretical predictions, reinforcing the understanding that the Sun will follow a similar path. In essence, the eventual depletion of core hydrogen is dictated by the laws of nuclear physics. There is no external factor or random process involved. It is simply the outcome of the fusion reactions that power the Sun. As long as fusion continues, hydrogen is consumed. When hydrogen runs out, fusion ceases, at least in the core, and the star evolves. This is why the Sun's fuel supply will run out. It is not a matter of chance or external events, but an unavoidable consequence of its internal processes. Once the core hydrogen is exhausted, the Sun must change. It cannot remain a main sequence star. Even before the final depletion of hydrogen, the Sun's increasing brightness will render Earth uninhabitable. The timescales involved are long by human standards, but brief on a cosmic scale. The story of the Sun's life is ultimately a story of fuel consumption. The process that makes the Sun shine also guarantees that it cannot shine forever. The finite nature of hydrogen fusion defines the Sun's lifespan and shapes its future. Understanding this fact provides insight not only into the fate of the Sun, but into the life cycles of all stars. In every case, the supply of nuclear fuel determines the duration of a star's stable life. For the Sun, that supply is limited, and the clock is running. In about 5 billion years, the Sun will undergo a profound transformation. The stable period of core hydrogen fusion that defines its main sequence phase will come to an end. Once the hydrogen in the core is largely exhausted, the balance that has held the Sun steady will break down, and the Sun will begin to evolve into a red giant. This process begins when the core, deprived of hydrogen fuel, can no longer sustain nuclear fusion at the current rate. With no more fusion-generated pressure to counteract gravity, the core will begin to contract under its own weight. As it contracts, the core will heat up further, reaching temperatures well above those seen during the main sequence phase. At the same time, the outer layers of the Sun will respond to the core's changes. Although fusion in the core will decline, a thin shell of hydrogen surrounding the core will still contain enough material for fusion to continue there. The increasing temperature of the contracting core will heat this surrounding hydrogen shell to the point where fusion can resume, but in a different configuration. This shell burning generates large amounts of energy, even more than the Sun produced during its stable phase. The energy released from this shell will push outward, causing the Sun's outer layers to expand significantly. As these layers spread out into space, they will cool, giving the Sun a reddish hue. This is what defines a red giant, an expanded, cooler, more luminous star. As the Sun swells, its radius will increase dramatically. Current models suggest that the radius of the red giant Sun could reach out as far as Earth's current orbit, or even beyond. Mercury and Venus will almost certainly be engulfed. The fate of Earth is less certain, as there are complex interactions between solar mass loss, tidal forces, and orbital changes that affect whether Earth will be swallowed or simply roasted. Even if the planet is not physically consumed, the conditions on Earth will become completely uninhabitable. As the sun grows, its luminosity will increase by a factor of several thousand. Long before the sun reaches its maximum size, Earth's oceans will have boiled away. The atmosphere will be stripped, and the surface will be scorched to hundreds or thousands of degrees Celsius. The timeline for these changes is well understood. The sun is about halfway through its 10 billion year main sequence lifetime. In roughly 1 billion years, rising solar luminosity will make Earth's surface temperatures too high for complex life. As the sun continues to brighten, Earth's habitability will decline. By the time the sun enters its red giant phase in about 5 billion years, the planet will be lifeless. During the red giant phase, the sun will lose a significant portion of its mass. The expansion of the outer layers will make them only loosely bound to the sun's gravity. Strong stellar winds, streams of charged particles, will carry away material into space. Over the course of this phase, the sun could lose as much as 30 to 40% of its original mass. This mass loss will affect the orbits of the remaining planets. With less mass at the center of the solar system, the gravitational pull on the planets will weaken. Their orbits will expand. Depending on how these effects interact with the sun's expansion, Earth could either be engulfed or escape slightly outward. Either way, the planet will be completely sterilized. Meanwhile, in the contracting core, temperatures will eventually reach about 100 million Kelvin. This is hot enough to ignite helium fusion, the process by which helium nuclei fuse into carbon through the triple alpha process. The onset of helium fusion will bring a new, though relatively brief, period of stability to the core. When helium fusion begins, the sun will temporarily shrink somewhat and settle into a new equilibrium, with helium burning in the core and hydrogen shell burning continuing outside it. This phase will last for a few tens of millions of years, far shorter than the main sequence phase. Eventually, the core's helium supply will also run out. The sun is not massive enough to fuse heavier elements beyond carbon and oxygen. Without new fusion processes to sustain pressure against gravity, the core will contract again, while the outer layers are pushed away. The entire red giant phase, including the helium burning period, is expected to last on the order of 1 to 200 million years, a brief time compared to the billions of years of main sequence life. The physical mechanisms driving this process are well established. They are based on stellar structure equations that account for the balance of forces, energy generation rates, opacity of plasma, and the thermodynamic properties of gases at different temperatures and pressures. Observations of other stars provide a clear view of what is to come. Astronomers can observe red giants at various stages of evolution in our galaxy and others. The patterns of brightness, temperature, size, and mass loss match the predictions of stellar models. The Sun, being an average mass star, will follow this path with a high degree of certainty. By observing star clusters, groups of stars that formed at the same time, astronomers can map the life cycles of stars of different masses. These observations confirm that stars like the Sun inevitably pass through a red giant phase as they transition from core hydrogen burning to later stages of evolution. It is also important to recognize that the Sun's transition into a red giant is not a single event, but a gradual process. The core contracts slowly. The shell fusion accelerates. The outer layers expand over tens of millions of years. For any observers living at that distant future time, if any exist, the changes would appear slow, unfolding over many human lifetimes. The final expansion into a red giant is a natural consequence of the finite supply of hydrogen fuel and the well-understood physics of fusion, gravity, and stellar interiors. There is no avoiding this outcome. The Sun's future is determined by its current mass and composition. Eventually, after the red giant phase, the Sun will shed its outer layers entirely, creating a planetary nebula and leaving behind a dense white dwarf core. But that is a later stage. The red giant phase is the most dramatic transformation the Sun will undergo, an inevitable expansion that will reshape the solar system and end the possibility of life on Earth. As the Sun begins its transformation into a red giant, the effects on Earth will be catastrophic and irreversible. Long before the Sun reaches its maximum size, the gradual changes in its structure and output will render the planet uninhabitable. Understanding this process requires a close look at both the Sun's evolution and Earth's response to it. The key factor is the Sun's increasing luminosity. As the core contracts and shell hydrogen fusion accelerates, the Sun's total energy output will rise dramatically. Currently, the Sun's luminosity increases by about 1% every 100 million years. In the short term, this seems slow, but over geological timescales, it has major consequences. In roughly 1 billion years from now, still well before the onset of the true red giant phase, the Sun's increased brightness will push Earth's climate beyond a critical threshold. The additional energy input will raise surface temperatures, accelerating the evaporation of water from the oceans. As water vapor increases in the atmosphere, it will enhance the greenhouse effect, trapping even more heat. This runaway greenhouse effect will lead to a rapid rise in global temperatures. Once average temperatures climb high enough, the oceans will begin to boil. Water vapor will dominate the atmosphere, making conditions similar to those of present-day Venus. At this point, complex life on Earth will no longer be sustainable. High temperatures will destroy most ecosystems. Photosynthesis will cease as plants die off. Oxygen levels in the atmosphere will decline. Eventually, even microbial life will struggle to survive. As the oceans evaporate, large amounts of water vapor will reach the upper atmosphere, where solar ultraviolet radiation will break apart the water molecules. The resulting hydrogen atoms, being light, will escape into space. Over time, Earth will lose the majority of its water. This desiccation process is irreversible. Once the oceans are gone, they cannot be restored. Without liquid water, Earth's surface will become dry and barren. As the Sun continues its evolution toward the red giant phase, these effects will intensify. The outer layers of the Sun will expand, and its luminosity will rise to several thousand times its current value. Surface temperatures on Earth will reach extreme levels, possibly exceeding 1,500 degrees Celsius. At such temperatures, not only water, but also many rock-forming minerals will begin to melt. The crust may partially liquefy, creating a hellish environment of molten rock and toxic gases. The atmosphere, now thick with carbon dioxide and other greenhouse gases, will expand and be gradually stripped away by the enhanced solar wind. As the Sun loses mass, its gravitational pull on Earth will weaken slightly, causing Earth's orbit to move outward. However, this outward drift will not be enough to save the planet. Current models suggest that Earth will either be engulfed by the expanding solar envelope or left as a scorched, lifeless rock just outside the Sun's swollen outer layers. The exact outcome depends on complex interactions between tidal forces, mass loss from the Sun, and changes in Earth's orbit. If Earth is engulfed, the planet will be subjected to intense friction and drag as it moves through the Sun's outer atmosphere. This interaction will quickly spiral the planet inward, and Earth will disintegrate, its material absorbed into the Sun. If Earth escapes engulfment, it will still face total sterilization. Any remaining atmosphere will be stripped away. The surface will be bombarded with intense ultraviolet and X-ray radiation. No life, as we understand it, will survive. These predictions are based on detailed models of stellar evolution and planetary dynamics. Observations of other red giant stars confirm that such expansions and mass loss processes are common. Planets orbiting close to their stars are often destroyed or rendered uninhabitable during this phase. It is important to understand that the changes leading to Earth's destruction will not be sudden. They will unfold over hundreds of millions of years. However, once the critical thresholds are crossed, the process will accelerate. The loss of oceans, the collapse of the biosphere, and the stripping of the atmosphere will occur in geological moments compared to the Sun's overall lifespan. From a human perspective, these events lie in the distant future, billions of years ahead. But in astronomical terms, they are part of a predictable and inevitable sequence. The forces at work are well understood. The physics of fusion, gravitational dynamics, and the thermodynamics of planetary atmospheres. No known natural process can halt or reverse the Sun's evolution, nor can any technology currently imagined prevent the outcome for Earth. The fate of the planet is tied to the life cycle of its star. This understanding is based on a century of progress in astrophysics. Theories of stellar evolution, confirmed by observations of stars at various stages, provide a consistent and reliable picture of the Sun's future. The processes that will transform the Sun into a red giant and destroy Earth are not speculative. They are grounded in established science. The destruction of Earth's habitability long before the Sun reaches its maximum size is also important to recognize. Many people think of the red giant phase as the moment of catastrophe. In reality, the critical loss of habitability occurs much earlier, as the Sun's slow brightening triggers the runaway greenhouse effect. The Earth of 5 billion years from now will be a very different place, lifeless, barren, and likely molten on its surface. Whether engulfed by the Sun or left as a dead world in an expanded orbit, its fate is sealed. This scenario applies not only to Earth, but to many planets around other stars. The life cycles of stars dictate the long-term habitability of their planetary systems. Understanding the fate of Earth provides insight into the broader question of planetary habitability in the galaxy. In summary, as the Sun becomes a red giant, Earth will undergo extreme and irreversible changes. Rising temperatures, ocean loss, atmospheric stripping, and intense radiation will sterilize the planet. Whether engulfed or left behind, Earth will no longer support life. These outcomes are certain, dictated by the fundamental physics of stellar evolution. When the Sun exhausts the hydrogen fuel in its core, a new phase of nuclear fusion begins. This phase is known as helium fusion, or more specifically, the triple alpha process. It represents the Sun's final opportunity to sustain energy production through nuclear reactions. The helium fusion stage is shorter and less stable than the long-lasting hydrogen-burning main sequence phase, and marks one of the last chapters in the Sun's active life. As the Sun transitions into a red giant, the core undergoes significant changes. The hydrogen in the core is depleted, replaced by an inert mass of helium ash. Without the outward pressure provided by hydrogen fusion, gravity forces the core to contract. This contraction increases both the core's density and its temperature. Temperatures in the contracting core climb rapidly, from about 15 million Kelvin during the hydrogen burning phase to over 100 million Kelvin. This extreme heat is necessary because helium nuclei, known as alpha particles, carry a double positive charge. As a result, the Coulomb barrier between helium nuclei is much greater than that between protons. Only at these elevated temperatures can the thermal motion of helium nuclei overcome the electrostatic repulsion and allow fusion to occur. The fusion of helium proceeds through the triple alpha process. The name refers to the fact that 3 helium-4 nuclei, alpha particles, are required to form 1 carbon nucleus. The process occurs in 2 steps. First, 2 helium-4 nuclei collide to form an unstable beryllium-8 nucleus. This intermediate nucleus has a very short half-life, about 10 to 16 seconds, and will quickly decay back into 2 helium nuclei unless a third helium nucleus collides with it during this brief window. If a third helium nucleus interacts with the unstable beryllium-8 nucleus before it decays, the result is a stable carbon-12 nucleus, along with the release of energy. This reaction releases less energy per unit of mass than hydrogen fusion, but the temperatures and densities involved in this phase compensate, allowing the core to generate significant energy. However, helium fusion is not as efficient or as long-lived as the hydrogen fusion phase that sustained the Sun for billions of years. The onset of helium fusion is not a gradual process. In stars of about 1 solar mass, including the Sun, the core becomes degenerate before helium fusion begins. Electron degeneracy pressure, a quantum mechanical effect, supports the core against further collapse, independent of temperature. As the core temperature climbs, it reaches the point where helium fusion can begin. In a degenerate core, however, the temperature increase does not lead to expansion because the core's support is provided by degeneracy pressure rather than thermal pressure. As a result, once helium fusion starts, it proceeds in a runaway fashion, producing a burst of energy in what is called the helium flash. During the helium flash, a large amount of energy is released in a short time. In the Sun's case, the total energy output during this event is enormous, briefly reaching values many thousands of times the Sun's current luminosity. However, because the energy is absorbed and redistributed by the overlying layers of the star, there is no sudden external change visible at the surface. The helium flash ends the degenerate state of the core. The core expands and cools slightly, reducing the fusion rate and stabilizing the star for a new phase of evolution. During this phase, the Sun will burn helium in its core and hydrogen in a surrounding shell. This new period of relative stability will not last nearly as long as the main sequence phase. While the hydrogen burning phase of the Sun's life lasted about 10 billion years, the helium burning phase is expected to last only about 100 million years, just 1% of the main sequence lifetime. During this phase, the core will steadily convert helium into carbon, with smaller amounts of oxygen forming through further fusion reactions. The Sun is not massive enough to sustain the fusion of elements heavier than carbon. Only stars with initial masses greater than about 8 times that of the Sun can proceed to fuse heavier elements like neon, silicon, or iron. As helium fusion continues, the same process that occurred during the hydrogen burning phase repeats itself on a faster timescale. Helium is consumed, helium ash builds up in the core, and eventually the helium runs out. Once core helium is exhausted, fusion can continue only in shells surrounding the core. A hydrogen-burning shell outside the helium-burning region and possibly a helium-burning shell above the carbon-oxygen core. With no new source of core energy, the core contracts again, heating further but never reaching the conditions required for the fusion of carbon in a star of this mass. The outer layers of the Sun will respond by expanding further. The Sun will re-enter an unstable phase known as the asymptotic giant branch, AGB, characterized by thermal pulses and increasing mass loss. The expansion of the Sun during this late giant phase will be dramatic. The radius will increase again, possibly exceeding the orbit of Earth by a large margin. Surface temperatures will fall, but the overall luminosity will remain very high due to the vast size of the star. During this final expansion, the Sun will lose mass at an accelerated rate through powerful stellar winds. Observations of AGB stars and planetary nebulae in our galaxy show that this is a common fate for stars of about 1 solar mass. The loss of mass will significantly affect the orbits of the remaining planets, which will drift outward. However, for Earth, already sterilized or consumed during earlier phases, this change will have little practical significance. The core, now composed primarily of carbon and oxygen, will continue to contract and heat. But without a sufficient mass to ignite carbon fusion, the process will halt. The Sun will not explode as a supernova, as only much more massive stars can achieve the necessary conditions for such an event. Instead, the Sun will approach the final stages of its life. With helium fusion complete and no new fusion reactions to maintain outward pressure, the outer layers will continue to drift away into space, forming a planetary nebula. The remaining core will become a white dwarf, an object composed of degenerate matter supported against further collapse by electron degeneracy pressure. The helium fusion phase represents the Sun's last major opportunity to sustain nuclear fusion. It marks the transition from a life-giving star to a dying remnant. Though brief compared to the main sequence phase, this period is a necessary and inevitable stage in the Sun's evolution, governed by the physics of stellar interiors and the limited fuel supply available to stars of this mass. After the Sun's helium-burning phase ends, it will enter one of the most dramatic stages of its life cycle. The fusion reactions that sustained the Sun for billions of years will no longer be possible in its core. The remaining core will contract, while the outer layers of the star become unstable and are gradually lost to space. This process leads to the formation of a planetary nebula and a white dwarf, the Sun's final fate. When helium in the core is depleted, no further fusion reactions can occur at the Sun's mass. The core will then consist mostly of carbon and oxygen, with temperatures rising as it contracts under gravity. However, the Sun is not massive enough to ignite carbon fusion. In more massive stars, continued contraction of the core can eventually reach the temperatures and pressures needed to fuse carbon and heavier elements. but this requires a stellar mass of at least 8 times the mass of the Sun. The Sun falls far short of that threshold. Without further core fusion, there is no new energy to resist gravitational collapse. The carbon-oxygen core will shrink further, increasing in temperature and density, while the outer layers of the Sun respond in a different way. Hydrogen and helium fusion will continue for a time in shells surrounding the inert core, creating pulses of energy that drive strong stellar winds and eject material outward. The star will enter what is known as the asymptotic giant branch, AGB phase. In this phase, the Sun will expand once again, possibly becoming even larger than during its earlier red giant phase. The outer layers will be loosely bound and highly unstable. Periodic helium shell flashes, brief bursts of intense fusion in a thin layer, will cause the star to pulse and shed large amounts of mass. These pulsations, combined with strong stellar winds, will gradually strip the Sun of its outer envelope. Over the course of tens of thousands to hundreds of thousands of years, the Sun will lose much of its mass. The rate of mass loss is expected to reach up to 10 to 7 solar masses per year at its peak, driven by radiation pressure on dust and gas in the expanding outer layers. The ejected material will form a planetary nebula, an expanding shell of ionized gas surrounding the hot, exposed core of the star. Despite the name, planetary nebulae have nothing to do with planets. The term was coined by astronomers in the 18th century because the round, glowing shapes of these nebulae in small telescopes resembled planets. As the planetary nebula forms, the Sun's core, now a dense, hot object composed of carbon and oxygen, will be exposed to space. The intense ultraviolet radiation from this core will ionize the surrounding gas, causing it to glow brightly. The resulting planetary nebula will likely have a complex, often asymmetric structure shaped by magnetic fields, rotation, and any remaining stellar companions or planets. Planetary nebulae are relatively short-lived on cosmic timescales. They typically remain visible for only about 10,000 to 20,000 years before expanding and fading into the interstellar medium. The ejected material, enriched with elements produced during the Sun's life, will eventually mix with the surrounding gas and dust of the galaxy, contributing to the raw materials for future generations of stars and planets. The core of the Sun, no longer able to contract beyond a certain point, will stabilize as a white dwarf. The collapse is halted by electron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. This degeneracy pressure provides an effective resistance to further compression. The resulting white dwarf will be incredibly dense. A white dwarf with a mass similar to the Sun's will have a radius comparable to that of Earth. Its density will be on the order of 1 million grams per cubic centimeter, meaning a single teaspoon of white dwarf material would weigh several tons. The white dwarf will initially be extremely hot, with surface temperatures exceeding 100,000 Kelvin. However, without a source of ongoing fusion, the white dwarf will gradually cool over billions of years. It will radiate away its residual thermal energy as visible light, ultraviolet light, and X-rays. Over time, the white dwarf will fade, eventually becoming a cold, dark object known as a black dwarf. However, the universe is not old enough for any black dwarfs to exist yet. The cooling process takes many times the current age of the universe, trillions of years. It is worth emphasizing that the Sun will not explode as a supernova. Supernovae are the deaths of much more massive stars. In those cases, the core collapses beyond the white dwarf stage, forming a neutron star or a black hole, and the outer layers are blown away in a catastrophic explosion. The Sun does not have sufficient mass to undergo this process. Instead, its end will be far quieter, with mass loss occurring through winds and gradual ejection of outer layers. Observations of planetary nebulae and white dwarfs in our galaxy provide a clear preview of the Sun's fate. Thousands of planetary nebulae have been catalogued, showing a wide range of structures and properties. White dwarfs are also abundant and well studied. The characteristics of these objects match the predictions of stellar evolution models for stars of one solar mass. This process, the shedding of a planetary nebula and the formation of a white dwarf, represents the culmination of the Sun's life cycle. The Sun will pass from an active, life-sustaining star to an inert remnant. The planetary nebula will fade, and the white dwarf will slowly cool, a silent witness to the star's former energy and vitality. The transition from a helium-burning red giant to a planetary nebula and white dwarf is not only inevitable, but entirely predictable based on the well-understood physics of stellar structure and nuclear fusion. The Sun's final collapse and the dispersal of its outer layers are governed by gravity, quantum mechanics, and the immutable laws of thermodynamics. In the grand scheme of cosmic evolution, this is a common and natural process. Billions of stars in the galaxy have already followed this path. The future of the Sun is written in the stars that came before it. The final stage of the Sun's life will be as a white dwarf, a dense, compact, stellar remnant composed mostly of carbon and oxygen. After the planetary nebula fades, no further nuclear reactions will occur. The white dwarf will persist for billions, even trillions of years, slowly cooling as it radiates its remaining thermal energy into space. A white dwarf forms when a star with an initial mass of less than about 8 times the mass of the Sun reaches the end of its fusion processes. For stars of about 1 solar mass, like the Sun, core helium fusion produces a mixture of carbon and oxygen. When the helium supply is exhausted, no further fusion is possible because the core temperature and pressure are not sufficient to initiate carbon fusion. The inert core contracts under gravity until electron degeneracy pressure halts the collapse. Electron degeneracy pressure arises from the Pauli exclusion principle, a fundamental rule of quantum mechanics that states no 2 electrons can occupy the same quantum state simultaneously. As the core contracts, electrons are squeezed closer together, increasing their momentum. This generates an outward pressure that resists further compression, even at very high densities. The result is an object of remarkable density. A white dwarf with about 0.6 to 1.4 solar masses will have a radius roughly equal to that of Earth, about 7,000 kilometers. Despite its small size, its mass is comparable to that of the Sun, meaning that the density is enormous, around 1 million grams per cubic centimeter. A single cubic centimeter, roughly the size of a sugar cube, would weigh about 1 metric ton. The mass of a white dwarf cannot exceed a certain limit. This limit, known as the Chandrasekhar limit, is about 1.4 times the mass of the Sun. If the Sun had started its life with more mass, its core might eventually exceed this limit, leading to further collapse into a neutron star or triggering a supernova. However, because the Sun's initial mass is only about one solar mass, and because it will lose some fraction of this mass during the red giant and planetary nebula phases, the resulting white dwarf will remain well below this threshold. Once the white dwarf forms, no new energy is generated internally. The object is supported entirely by degeneracy pressure, not thermal or radiative pressure. Its temperature, initially very high, well over 100,000 Kelvin at the surface, begins to decrease as the white dwarf radiates away heat. The cooling of a white dwarf is a slow and gradual process. Without an internal energy source, its luminosity steadily declines. The object will first emit in the ultraviolet, then in the visible range, then in the infrared as it cools further. Because white dwarfs are small, they also have a relatively low surface area, which slows their rate of energy loss. The timescale for a white dwarf to cool to invisibility is extremely long, longer than the current age of the universe. It is estimated that it takes hundreds of billions to trillions of years for a white dwarf to cool completely. Since the universe itself is only about 13.8 billion years old, no white dwarf has yet had time to cool into the final dark state known as a black dwarf. The fate of the Sun's white dwarf remnant will thus be one of extreme longevity. Long after the planets have been destroyed or ejected, after the planetary nebula has faded into the interstellar medium, the Sun's white dwarf will remain. It will orbit the center of the Milky Way as a cold, dim stellar relic, a compact sphere of carbon and oxygen, slowly radiating away the last of its heat. White dwarfs are not merely theoretical objects. They are abundant in the galaxy and have been observed in great detail. The first white dwarf discovered was Sirius B, the faint companion of the bright star Sirius, located about 8.6 light-years from Earth. Spectroscopic studies of white dwarfs confirm their high densities, surface gravities, and compositions. White dwarfs exhibit a unique type of spectrum. The high gravity of these objects broadens spectral lines, and their atmospheres, typically composed of hydrogen or helium, produce distinct absorption features. Because white dwarfs cool over time, their temperature, luminosity, and color provide a record of their age. Astronomers have constructed white dwarf cooling sequences, diagrams showing how white dwarfs cool and fade over time. By comparing observations of white dwarfs in star clusters of known age, scientists can test models of white dwarf cooling and confirm predictions about their long-term evolution. Observations indicate that the majority of stars in the Milky Way will eventually become white dwarfs. Since low-mass stars are far more common than high-mass stars, white dwarfs will ultimately represent the dominant population of stellar remnants in the galaxy. Even after trillions of years, when the Sun's white dwarf has cooled to the point of invisibility, it will not be destroyed. White dwarfs are incredibly stable. Supported by quantum degeneracy pressure, they cannot collapse further unless they somehow gain mass, for example, by accreting matter from a companion star. Since the Sun will end its life as a solitary star, this scenario does not apply. The Sun's white dwarf will not explode, nor will it evaporate. It will remain, an inert mass of carbon and oxygen, locked in its final state for a duration far exceeding the current lifetime of the universe. This understanding is based on decades of detailed observations and theoretical work in stellar astrophysics. The equations of stellar structure, nuclear physics, and quantum mechanics provide a consistent and reliable picture of white dwarf formation and evolution. The Sun's future as a white dwarf is thus entirely predictable. It is the inevitable outcome of a star of this mass and composition. Once the final helium fusion ends, and after the planetary nebula disperses, the Sun will have reached the end of its life as an active star. From that point forward, its existence will be one of quiet, gradual cooling. The energy it once radiated will fade, and the star that gave life to Earth will become a cold, dark remnant, a white dwarf slowly fading in the depths of interstellar space. Only certain stars end their lives in supernova explosions. These spectacular events occur when the core of a massive star collapses under gravity, triggering an outward blast that expels most of the star's material into space. The Sun will not undergo such an explosive death. The reason is simple. The Sun lacks the mass required to initiate the processes that lead to a supernova. To understand why, it is necessary to review how mass governs a star's life and death. The core of a star is a furnace where nuclear fusion occurs. The balance between gravity and the pressure from fusion-generated energy defines the star's structure and stability. The more massive a star is, the greater its gravitational compression, and the higher the core temperature and fusion rate must be to counteract that gravity. Stars more than about 8 times the mass of the Sun can reach core temperatures exceeding several hundred million Kelvin. In these extreme conditions, fusion proceeds beyond helium. Such stars can synthesize heavier elements like carbon, neon, oxygen, silicon, and eventually iron through a series of increasingly short and intense burning phases. The fusion of each element releases energy, which helps support the star. However, when the core is composed of iron, no further energy can be extracted through fusion. Fusing iron nuclei absorbs energy instead of releasing it. At this point, gravity overwhelms any remaining pressure, and the core collapses catastrophically in a fraction of a second. This core collapse generates shock waves that trigger a supernova explosion. The outer layers of the star are blasted away, enriching the interstellar medium with heavy elements. The remnant core becomes either a neutron star or, if massive enough, a black hole. The Sun, by contrast, will never reach the conditions required for such a collapse. It began its life with a mass of about 1 solar mass, far below the threshold needed to progress beyond helium fusion. As it evolves into a red giant and sheds mass, its final mass will decrease even further. Once the Sun exhausts helium in its core, no additional fusion processes can occur. The core, composed of carbon and oxygen, will contract until electron degeneracy pressure halts further collapse. The Sun lacks the mass to compress the core to the point where carbon fusion could ignite. Because there is no collapse beyond this stage, the Sun's death will be quiet. It will shed its outer layers to form a planetary nebula and leave behind a white dwarf. No explosive supernova will occur. Observational evidence supports this understanding. Astronomers have studied many stars of various masses and mapped their life cycles. Massive stars are observed in late stages of evolution with heavy element cores. Stars with masses like the Sun's, never reach this state. Furthermore, the abundances of elements observed in white dwarfs and planetary nebulae match theoretical predictions for stars of this mass. No signs of the products of explosive nucleosynthesis, the creation of elements during supernovae, are found in such remnants. The underlying physics is also clear. The Chandrasekhar limit, roughly 1.4 solar masses, defines the maximum mass that a white dwarf can sustain before collapsing. The Sun's white dwarf core will be well below this limit. Even after helium fusion ends, the core will remain stable, supported by degeneracy pressure. This outcome is determined by the Sun's initial mass and by the processes of mass loss that occur during its giant phases. During the asymptotic giant branch phase, the Sun will shed a significant portion of its mass through stellar winds. The remaining core, after the outer layers are ejected, will weigh approximately 0.5 to 0.6 solar masses, far below the critical threshold for further collapse. The sequence of stages, main sequence, red giant, helium burning, asymptotic giant branch, planetary nebula, and white dwarf, is well supported by stellar models. Observations of star clusters, where stars of various initial masses can be compared at similar ages, confirm this pathway. Supernovae are among the most energetic events in the universe. They occur only in stars massive enough to form an iron core. For stars in the 8 solar mass range and above, the gravitational pressure can force the core beyond the degeneracy pressure of electrons, leading to collapse into neutron-degenerate matter or a black hole. The Sun's relatively small mass places it in a different evolutionary category. Its life will end in a much less violent way. The planetary nebula phase will be dramatic in appearance, but involves the gentle ejection of outer layers, not an explosive blast. From the perspective of planetary systems, this difference is significant. Planets orbiting massive stars often do not survive the shock waves and intense radiation of a supernova. By contrast, in systems like our own, the outer planets will remain in stable orbits, though altered by the Sun's mass loss. For Earth, however, the distinction will be academic. Whether engulfed or burned away during the red giant phase, the planet will be lifeless long before the planetary nebula forms. The stability of white dwarfs also means that the Sun's remnant will persist indefinitely. Unlike neutron stars or black holes, which can exhibit dynamic behaviors like X-ray bursts or accretion, white dwarfs evolve passively, cooling slowly over time. In cosmic terms, this quiet end is the norm for stars like the Sun. Observations indicate that roughly 97% of stars in the Milky Way will conclude their lives as white dwarfs. Supernovae, while spectacular, are rare by comparison. The lack of a supernova does not imply that the Sun's demise will lack significance. The ejected material from the planetary nebula will contribute to the chemical evolution of the galaxy, returning carbon, nitrogen, and other elements to the interstellar medium. These elements will enrich future generations of stars and planets. Thus, while the Sun will not explode, its legacy will endure in the composition of the galaxy. Its white dwarf remnant will orbit the Milky Way for trillions of years. The death of the Sun will have far-reaching effects across the entire solar system. While the processes leading to this transformation are gradual on human timescales, the final outcomes will be dramatic. The loss of mass, changes in gravitational forces, and dispersal of material into space will permanently reshape the orbits of the surviving planets and redefine the solar system's structure. As the Sun moves through its red giant and asymptotic giant branch (AGB) phases, it will lose a substantial portion of its mass. Stellar winds, powered by radiation pressure, magnetic activity, and pulsations in the star's outer layers, will expel gas and dust into the surrounding space. By the time the Sun sheds its planetary nebula and leaves behind a white dwarf, it is expected to have lost approximately 40 to 50% of its original mass. Gravitational force depends directly on mass. As the Sun loses mass, its gravitational pull on the planets will weaken. In response, the orbits of the remaining planets will expand. This is a simple consequence of orbital mechanics. To maintain angular momentum in a system where the central mass decreases, the orbital distances of objects must increase. The most immediate and severe effects will occur in the inner solar system. Mercury and Venus will likely be engulfed during the red giant phase. Their material will be absorbed into the Sun's outer layers or dispersed into space as part of the solar wind. The fate of Earth remains uncertain. Depending on the complex interactions between solar mass loss, tidal forces, and drag from the Sun's expanded envelope, Earth may be consumed or left in an altered orbit. Mars, just beyond the Sun's maximum predicted expansion, is likely to survive as a physical object, though its surface will be sterilized by intense heat and radiation. Its orbit will also shift outward. Farther out, the gas giants, Jupiter and Saturn, will experience orbital expansion as the Sun's gravitational pull weakens. Calculations suggest that the semi-major axes of planetary orbits could increase by roughly 30 to 50%. For example, Jupiter, which currently orbits at about 5.2 astronomical units, AU, may shift out to 7 or 8 AU. The specific changes depend on the timing and rate of mass loss, as well as any remaining gravitational interactions between planets. In addition to altering planetary orbits, the Sun's death will affect smaller bodies throughout the solar system. The asteroid belt, Kuiper belt, and scattered disk objects will experience reduced solar gravity and increased perturbations from the shifting orbits of the major planets. Many objects will be destabilized. Some will be ejected from the solar system entirely, becoming rogue bodies drifting through interstellar space. Comets from the Oort cloud, a distant spherical reservoir of icy objects, will also be affected. As the Sun's mass decreases, the gravitational binding of the Oort cloud will weaken. Some comets will be perturbed inward, potentially passing through the inner solar system, though by this time it will be a very different place. Others will escape into interstellar space. The solar wind and planetary nebula will also inject material into the interplanetary medium. The gas and dust expelled during the Sun's final phases will spread throughout the inner solar system and beyond, contributing to the local interstellar environment. This material, enriched with carbon, nitrogen, and other elements synthesized in the Sun, will eventually mix with the galaxy's gas and dust, providing raw materials for future star formation. While the planetary nebula phase is short-lived on cosmic timescales, typically lasting tens of thousands of years, its impact is significant. The structure of the solar system will already have been altered by the preceding mass loss. By the time the nebula dissipates and the white dwarf remains, the configuration of planets, minor bodies, and debris will bear little resemblance to the system as it exists today. One important consequence of these changes is the long-term stability, or lack thereof, of the surviving planets. With reduced solar gravity and altered orbits, The outer planets will be more susceptible to mutual perturbations. Over billions of years, gravitational interactions between Jupiter, Saturn, Uranus, and Neptune could destabilize the system further. Simulations of post-main sequence planetary systems suggest a range of possible outcomes. Some configurations may remain stable for trillions of years, while others may eventually lead to planet-planet scattering or the ejection of one or more planets. The details depend on initial conditions, planetary masses, and the precise history of solar mass loss. The Sun's white dwarf remnant will continue to exert gravitational influence, but at about half the mass of the original Sun, it will be a much weaker anchor. The dynamics of the surviving solar system will be dominated by the interplay between the planets themselves and the slow gravitational tides of the galaxy. Over extremely long timescales, tens of trillions of years, interactions with passing stars and molecular clouds in the Milky Way will further erode the solar system's stability. Some planets and smaller bodies will be ejected into interstellar space, while others may spiral inward toward the white dwarf or remain in distant orbits. In this distant future, the solar system will no longer resemble the orderly system of planets we know today. The familiar architecture, inner rocky planets, outer gas giants, asteroid belt, will be gone. In its place will be a more diffuse, altered system centered on a faint white dwarf. The fate of planetary systems like ours is a common subject of study in modern astrophysics. Observations of white dwarfs with debris disks, metal-polluted atmospheres, or surviving planetary companions provide direct evidence that many systems undergo similar transformations. The presence of planetary material around old white dwarfs confirms that planetary systems often survive, at least in part, after their stars die. In the case of the Sun, its legacy will include both the dispersal of elements into the galaxy and the altered configuration of the remaining solar system. The outer planets may endure for many trillions of years, their cold, frozen surfaces circling a fading remnant of the star that once powered their formation. These changes underscore the long-term impermanence of planetary systems. While the Sun's death will not be explosive, its gradual mass loss and transformation will fundamentally reshape the structure of the solar system. The process is inevitable and driven by well-understood physical laws. The Sun's death will scatter elements forged in its interior into space, contributing to the ongoing cycle of stellar birth and death in the Milky Way. The surviving planets, if any, will orbit a small, dense white dwarf in a vastly changed environment. In this way, the Sun's death will mark not just the end of an era for the solar system,
billions of stars in the Milky
but the
Way
beginning
and
of a new
beyond
phase
have
in the
already
ongoing
passed
evolution
through the
of
life
galaxy
cycle
that now awaits the Sun. The processes of stellar birth, evolution, and death are not unique to our solar system. They are universal, driven by the same physical laws across the cosmos. Understanding the future of the Sun and its inevitable decline places our own existence within the larger framework of cosmic history. The Sun is a relatively ordinary star, a G2V main sequence star with a mass and luminosity close to the average for stars in our galaxy. It is about 4.6 billion years old, approximately halfway through its stable hydrogen-burning phase. Stars of this type are common. They form from interstellar clouds of gas and dust, shine for billions of years, and eventually die in predictable ways. The cycle of stellar evolution began shortly after the universe itself formed. Following the Big Bang, the first atoms, primarily hydrogen and helium, emerged. Over time, gravity drew this material into clumps, forming the first stars. These early stars, known as population 3 stars, were much more massive than the Sun and had short, violent lives. They burned quickly, producing heavier elements through nuclear fusion and in their explosive deaths. The remnants of these first generations of stars seeded the interstellar medium with elements like carbon, oxygen, silicon, and iron. This enriched material provided the building blocks for subsequent generations of stars, including the Sun, and for the formation of rocky planets like Earth. The Sun is thus part of a cosmic lineage, one link in an unbroken chain of stellar evolution that stretches back over 13 billion years. Its birth was made possible by the deaths of earlier stars. Its life, governed by the fusion of hydrogen into helium, reflects processes observed throughout the galaxy. The end of the Sun's life, its expansion into a red giant, the shedding of its outer layers, and the formation of a white dwarf, is likewise not unique. Billions of stars of similar mass have already undergone these transformations. Astronomers observe planetary nebulae and white dwarfs throughout the Milky Way. These objects are the natural outcome of the stellar life cycle for stars in the Sun's mass range. The cosmic perspective emphasizes that our solar system is not isolated. It exists within a galaxy of hundreds of billions of stars, each with its own history and fate. Many of these stars have planets of their own. Studies of exoplanetary systems suggest that planet formation is a common process. The conditions that gave rise to Earth and to life are not necessarily unique. The inevitability of the Sun's death is part of this larger pattern. Stars are not eternal. They live and die according to their mass and composition. The processes involved, fusion, gravitational contraction, degeneracy pressure, are dictated by the fundamental forces of nature. The finite supply of nuclear fuel sets a limit on every star's lifespan. For the Sun, this means roughly 10 billion years of main sequence life, followed by a few 100 million years of red giant evolution, and finally trillions of years as a cooling white dwarf. During its life, the Sun has supported an entire planetary system. It has provided the energy that powers Earth's climate, weather, and biosphere. The history of life on Earth, from the earliest microbes to the complex ecosystems of today, has been possible only because of the Sun's steady output. When the Sun eventually dies, the solar system will be irrevocably changed. Earth will be destroyed or rendered uninhabitable. The remaining planets will drift in altered orbits around a faint white dwarf. The solar system's current order will give way to a new, quieter state. Yet even as the Sun fades, its material will contribute to the future of the galaxy. The elements forged in its core, carbon, nitrogen, oxygen, will be returned to interstellar space. These elements will become part of new stars, planets, and perhaps new life forms. The cycle of stellar birth and death will continue. Looking beyond the Milky Way, the same patterns unfold in every galaxy. Stars are born from interstellar clouds, shine for varying lengths of time, and die, enriching the cosmos with heavier elements. The universe is shaped by these ongoing processes. On even larger scales, the expansion of the universe itself will affect the fate of stars. Over trillions of years, star formation will slow as the supply of gas is depleted. The brightest galaxies will dim. The remaining stars will age and die, leaving a universe filled with white dwarfs, neutron stars, and black holes. Eventually, the universe may reach a state of heat death, where all thermodynamic processes cease. The stars we see today, including the Sun, will be long gone. Yet their influence will persist in the matter they contributed to the cosmos. For now, the Sun remains stable, continuing its middle-aged phase. Humanity exists during a relatively brief window in this timeline, after the formation of the solar system, but before the Sun's decline. The conditions that support life on Earth are transient on cosmic timescales. Recognizing this broader perspective highlights the fragile nature of planetary habitability. It also underscores the connections between stars, planets, and life. The elements in Earth's crust, oceans, atmosphere, and even in human bodies were forged in stars. We are, in a very real sense, products of cosmic evolution. The future of the Sun is written in the stars that came before it. Billions of stars have lived and died, following the same path. The observations of planetary nebulae and white dwarfs scattered throughout the galaxy offer a preview of the solar system's distant future. In the end, the Sun's fate is not an anomaly, but an expression of universal processes. Its life, death, and legacy are part of the ongoing evolution of the cosmos, a vast story unfolding over billions of years. Good night.